see it now?
Yeah.
No. Yeah. Okay. So the top is the coat. Wheel that down. So here, this is blue filter, and then there are another 16 for each other filter. So lots of graphs. But like when you see this very slight, it looks like comp 1 seems to have more scatter with everyone, and then I think comp 5 might be the best one, but like the comp 5 to 1 is still scattered, but that's comp 1's fault, right?
Yeah. What you're doing here is very standard.
Yeah. So, and then I did do the light curves all with all the different comps as well, so that this tab might show up. This is with comp 5 seems to be the best. Now, comp 5 did have one egregious outlier, which caused it to have a bigger standard deviation. That one outlier is like you can only see it if you plot. Like I think it must be a bad image. I'm thinking of just going back and finding that image and tossing it because it was just one that was over by phase 8. But the light curves seem to look better for comp 5. Comp 5 is the second one in each row of these guys.
Yep.
And the other comps look more scattered, I think. It's sort of a subjective thing.
Yeah. What is, I can't read the numbers on the graph.
Oh, sorry. It's phase versus flux. So it's by the phase of the target.
Richard, this is an eclipsing binary, right?
And then the flux is normalized. I mean, that was another subjective thing too. We just said, well, it looks like it's not eclipsing between 0.3 and 0.4 in phase. So we'll set that average value between 0.3 and 0.4 to be 1, and that'll normalize it.
Yeah, perfectly reasonable.
Oh, that's good to hear it's reasonable, because there's a lot of decisions that I just feel like we're sort of making by looking at things with eyeballs rather than
if that out of eclipse area is normalized to a flux of 1, what's the plus or minus scatter in that area?
I'm not sure.
I can't read the graph.
Let's see which graph I can blow stuff up a little bit. Maybe let me see if that works.
Pick a good one.
Let's see. I'll pick one. Here's. That might get bigger a little bit. I'll just do one particular one. And then I can make this bigger. So I'll stop sharing, and then I will share again and use the preview window. That's a bigger version, sort of pixelated. So that's the phase, and then we said that between 0.3 and 0.4, I don't know if you can see me marking this up.
No,
but like right around here. Yeah, we were like, well, right around there, it looks like it's not eclipsing. So take the average flux in that region and set that to be equal to 1.
Mm-hmm.
And then the stuff that's on top of that is stuff that was bigger than average, and the stuff that's less than that is.
That's actually, you know, that box that Drew goes from about 0.95 to 1.15 or 1.05. So we're talking a plus or minus 5%, which is probably 2 sigma. That's pretty good.
That's good.
And
so I think that's good. Comp 5 might be our winner. So the thing to look for from here, the thing that you were seeing with Comp 3 and Comp 4 is to see if we can find a way to get full width at half maximum for the stars in the image and any stars with a bigger than average full width at half maximum are likely to be saturated.
Yeah.
So that's sort of another way to check for it. That's really cool to know about.
Yeah.
But I just got to figure out how to get that.
When you're plotting, comp 1 versus comp 2, if you see big scatter, bigger than normal, then one of those two stars is the offender, and just say there's something wrong with it. I'm not going to use it. But this is good, and the other thing about that plus or minus 5% that you're seeing, the signal to noise ratio, which AIP puts out on the bargains and comp in your B band anyhow are 200 to 1, and you kind of expect the 1 sigma scatter to be roughly 1 over the signal to noise ratio within a factor of 2 or so. So that hangs together with what we're seeing here. Your suspicion that like that outlier that is right around phase 0.7, it's way above the curve.
Actually, that's not even the one. There's a bigger one that's not shown just because it's not. I put all the graphs on the same scale. There's a bigger one that's 5.8 that's like up even higher.
Yeah, one of the other things that most beginning photometrists are strongly advised to do is flip through your images and look at every single image, which seems a little mind-numbing when you've got 500 images, but it will show you the ones that something went wrong. In the sample that you sent me, there are a couple that are badly out of focus, way bad.
Okay.
The stars all look like donuts. And there are a few that are affected by clouds. There's some where there is no star at all. And unfortunately, most photometry routines, when you tell it, my target is located here and my comp is located here, well, it remembers the pixel coordinates. And when you bring up a new image, it'll look at those pixels, even if there's nothing there. And it'll report, data that is just, crazy. There's one other thing I noticed is on several nights, it looked like the image was rotated, maybe just a few degrees compared to the night before. That probably means somebody was doing maintenance at LCOGT. Some photometry routines can handle that. Almost all of them can handle if the image has been shifted left, right, up, down. It'll go find your stars again if they didn't shift too far. But a lot of them have a real problem with image rotation. And you may flip through the images and kind of watch for that rotation also. And you may want to figure out how to measure the individual image by hand to make sure that is it AIJ, Astro Image J that you're using?
Well, so we used Astro Image J to look for comps. Then after we had found them, and we also used Astro Image J to test for exposure times. But then our solar siblings returns to us those 6 photometry types from the images. So after we had looked through enough of them to just to find our comps and exposure times, we've been using just those files full of numbers that have star coordinates and whatnot. However, we can correlate those files with the images. So if we flip through images and find some that we don't want to use, we can also get rid of those associated files.
Yeah, that would probably be a good thing to do. It may get rid of some of the outliers. And it's also enlightening for the students to see examples of things that can just go wrong. Why are some of those images badly defocused? Who knows? But, stuff happens in the night.
Yeah. Okay. Yeah, no, that's awesome. That'll be really helpful.
And as you flip through, say, pick a particular color band, and you flip through, and you'll see, boy, here's an image, looks good, and then all of the stars are way fainter than before. Well, that means clouds or fog or something was going on. And occasionally you'll see where the stars are fading away at the top of the image, but not at the bottom. You're at the edge of the cloud.
Interesting.
And that's bad for photometry, obviously.
That might be a good scavenger hunt type activity for them to do.
Yeah. If you've got
make it fun,
if you've got something to let you click through the images, you can, look at each one in 5 seconds. And so you can go through 500 of them in, a half hour, no problem.
Yeah, cool. We'll do that.